is our part 2 of our little series about precipitation reactions. So in the first part of these two that we looked at just kind of being able to figure out what happened if we combine two aqueous solutions together. We looked at solubility rules, tried to figure out if we could predict what the product would be, and potentially what kinds of leftover ions might be left over in solution. So this particular video, we're going to take a look more in depth at how do we represent precipitation reactions with different types of balanced chemical equations. These are taking the kinds that we've already done and going a little bit further to be a little bit more accurate on the atomic molecular level to represent what's really going on in a solution. So just as by way of review, precipitation reactions, you take two aqueous solutions, so two solutions where you've got some different chemical solutes that are dissolved in water, and then you combine them together. And then sometimes you get interesting solids that form from those interactions. Those solids are called precipitates. They usually look muddy or cloudy, and eventually they usually settle down to the bottom of a test tube. I picked some kind of fun colored ones here to show. Keep in mind that not every reaction between two solutions forms a precipitate, and lots of precipitates are really actually just kind of a boring white color. I try to pick kind of fancy colored ones to show you just because it's visually just more interesting. Keep in mind the two things that we need to deal with this. How do you know what that precipitate is? How do you know what the green or the orange or the black stuff is? Well, a couple things. Number one, you probably have something called solubility rules. Solubility rules are either like a handout, or maybe they're you Google it, you look it up in the back of the book, something like that. But it's a list of rules that help you predict whether or not a particular compound will be soluble or insoluble. And then number two, you have to do a little bit of background work to kind of make sure you know what insoluble and soluble means. It's a little bit backwards here, but the term insoluble means it's going to form the precipitate. It does not dissolve in water, so it's going to be there as a cloudy solid and will settle out. If it's soluble, that means that it can dissolve in water and it's going to stay in its ionic form. So that's a little bit of a different kind of a situation vocabulary word that sometimes students can get tripped up on. So insoluble against the precipitate. Soluble means that it's the one that's still remaining dissolved. It looks sort of unreacted. So in terms of writing chemical reactions, my cat's coming to visit. He's in my lap. Awesome. You want to say hi? Hello. So it's the problem with doing these at my house. So I got cat hair on my face. When we're writing chemical equations, the first step that when we typically write them is like you've always written them before. We write that balanced chemical equation. It looks like molecules. You have to balance the charges. You have to use subscripts and parentheses and all that kind of good stuff. That type of reaction, like we've always done, sometimes it's called a formula equation or a molecular equation because it makes all the chemical compounds there look like they're in their molecule form. The problem is things that are aqueous aren't truly molecules, so we want to kind of go the next step to be able to more accurately represent it. Molecular equations or balanced chemical equations, our regular kind, are really useful for a couple of things. Number one, they're really easier for us sometimes to predict what our products are going to be or to be able to write names for things. Number two, it tells you the names of the solutes. It actually gives you the real chemical formula, whatever we use to make those solutions with in the first place. And then number three, most importantly, is that it gives us the ratios. By writing and balancing that equation out, we have a really accurate picture of the numbers of things that are required to react with one another. So this is true on the atomic or molecular level, like 2 atoms of this and 2 molecules of that. But as we get into the next chapter, when we're starting to predict quantities, it's molar quantities. It gives us that 1 mole of this reacts with 2 moles of that to make 2 moles of the other thing. That becomes really, really valuable for us. So just because we're moving forward to these kind of other more detailed types of reactions doesn't mean that molecular equations don't have a use. They absolutely do, which is why we teach them first. So in terms of when we're trying to do a particular type of a balanced equation, by way of reviewing, we need to be able to predict products. So here is an example that we'll use here in the first couple slides. So we're going to react a solution of cobalt chloride, which is a glorious pink color, and sodium hydroxide together, which is just a kind of a clear, doesn't look like much kind of solution. What could be our 2 products? So again, by way of review, you mix and match. You kind of do your first and last together, and then you do your 2 middle ones, the inside-outside kind of rule. And we would get something called cobalt hydroxide, and we get sodium chloride. And the next step then would be to figure out which of these would be our possible precipitate. So you'd pull out your handy-dandy solubility rules, ta-da! Or you might remember the shortcut that I taught you, the Nakel-Noso shortcut, that things containing sodium, ions and their families, chloride ions, nitrate ions, or sulfate ions tend to be soluble. They're not a precipitate. You can take a look at this equation. You probably can figure out which one it is. NaCl is definitely going to be our soluble one. It's got both sodium and chlorine in it. But that cobalt hydroxide, if we have a precipitate, that's going to be it. By the way, we do need to remember to balance our equation as we do this. So by way of review, we would have to have 2 NaOH and 2 NaCl's because the charge of cobalt is a 2+, so we get a little bit of fanciness there. So there you go. There's our balanced chemical equation, also known as a molecular equation, and it would have all of the balanced charges in there, it would have coefficients in there, and then it would have physical states, especially the state of the precipitates, kind of the important one for us. All right, so if we want to go further than this, we want to actually more accurately represent what's going on. The molecular equation only shows us these things as molecules, as combined. The problem is when things dissolve in water, they dissociate into ions. So we need to more accurately represent this. And this is kind of like an exploded diagram. We're going to take each one of our things that has AQ after it and show it as ions, because it truly is. These are dissociating into cobalt ions, for example, and chloride ions. It is not staying as little COCl2 molecules. It is separating out into the two separate kinds of ions. A couple things to kind of note here. Make sure that if you have a subscript that comes from balancing charges, that it becomes a coefficient down in this kind of exploded diagram, this ionic diagram that we're doing, ionic equation. Same thing over here. If you have a coefficient out in your molecular diagram, that's a little bit more straightforward, your molecular equation. That's going to become coefficients down here in your ionic equations as well. So I have 1 cobalt ion, I have 2 chloride ions, I have 2 sodium ions, and then I have 2 hydroxide ions. That's my reactants that's actually going in there. So my solutions don't contain molecules, they contain these 4 different types of ions. And when I throw them together, it turns out that the cobalts and the hydroxides really strongly bond to one another. So those are the ones that form that solid. Those cobalts and hydroxides see each other across the room, chemically speaking, they bond together, and then they form the solid and they literally fall out. The other things, the sodiums and the chlorines, are still hanging out. They don't mind one another. They're friends with each other. They're attracted, but they're also just hanging out in the water molecules. So we keep them separate because that's soluble. So the soluble ones stay separated out. And if you've done it right, your ionic equation will already be balanced. And if you take a look at this really closely, I've got the same numbers and types of atoms on both sides of the equation. So keep in mind, here's the critical rule for writing ionic equations. This would be a complete ionic equation in this case because I'm showing everything. Number 1, aqueous compounds, anything that's soluble, dissolves in water, and separates, dissociates into its ions. Don't forget to include, to change your subscripts basically into coefficients when you're writing your ionic equations out. So you can't just ignore those are there, and they give you important ratio information. Precipitates, on the other hand, are insoluble, and they're the ones that stay in molecular form. So that's that cobalt hydroxide. Notice how when I wrote this ionic equation, I did not separate that one out because those two are so tightly bound to each other that they stay stuck and they form that precipitate and settle on down. So those are the key big ideas. If you see something that's aqueous, you write it as ions. If you see something that's solid or insoluble, you would write that as a molecule to kind of keep it stuck together. Okay, so big rules here. The couple of things that you need to get. When something's soluble, it exists as ions, not molecules, and there's some kind of reasons for that. The water molecules get in there and they start sort of pulling things apart. And it turns out those ions are perfectly happy going with the water molecules and kind of spreading throughout solution. Those things, the reason why we can't see them is because individual ions are so small and they spread out so evenly throughout the water, they're usually invisible to us. The only times that they're at all visible is when you have ions that are colored, like copper ions tend to form a blue solution and nickel ions tend to form a green solution. But those solutions are clear, they're transparent, you can see right through them like Kool-Aid. They're not cloudy, they don't have any sort of smoky type of a precipitate that's in there. So precipitates, however, on the other hand, right, those are the ones that are molecular. Those things stick to each other more than they stick to the water molecules. And in fact, the molecules stick to each other, they sort of clump together and form that sort of cloudy or muddy looking precipitate that if you give it enough time, they will settle out to the bottom and it looks kind of silty when it's down there. Okay, so here's a practice opportunity for you to see if you can kind of do it correctly. These are unbalanced equations. The top one, I've given you the products. The bottom one, you have to predict the products. So in order to do this, the best for you, what I would do is hit pause, go Google out a set of solubility rules if you don't have yours from class, and see if you can figure out what these things are. So number 1, separate anything that's aqueous into ions and then keep the solid together. Keep the precipitate as one thing. So hit pause, See if you can scratch this out on a piece of paper, and then I'm going to work through it here with you in a second. 3, 2, 1, here we go again. So here we are. I'm going to do this top one out. Number one, I got to balance my equation. Did you remember to do that? Probably not, right? But I got to balance my equation because over here I've got 2 nitrates and 2 potassiums, so I need to have a 2 out front here, so balance it first. Next thing, calcium nitrate is aqueous, so there it is split out into its 2 separate ions. What about potassium carbonate? Aqueous as well, so we split that out. Hopefully you remember to include some coefficients down in here. There's 2 nitrates in the calcium nitrate, and there's 2 potassiums in the potassium carbonate. Again, those ones are there from balancing charges, so that's why we have to put those out as coefficients. The 3 that goes with the nitrate and the 3 that goes with the carbonate, those are from the polyatomics, so those stay together as a unit. Remember, polyatomics don't break apart. So that's where those 3s came from, and that's why those are not turning into some sort of a coefficient. Okay, over on the right, the potassium nitrate is soluble. Rule number 1 is that all nitrates are soluble. So that one is going to explode out into our ions. So we have 2 potassium ions and 2 nitrate ions because this coefficient, this pink one out in front, has to kind of distribute across everything. And then here's calcium carbonate. Calcium carbonate is a rather boring looking white precipitate. It stays as itself, so there you go, CaCO3 as a solid. Okay, the bottom one here. Definitely a little more challenging because I didn't give you the products. So hopefully you remember that in this kind of a double displacement reaction that the outside 2 go together and then the inside 2 go together. So our possible products would be iron and phosphate, and our other product would be lithium and acetate, something like that. So here we are. If you write these formulas out, again, checking and balancing your charges, these would be the correct formulae for our products. Fe3PO4, iron's a 2+, phosphate's a 3-, bet you forgot that. And then over on the right we have lithium acetate. Lithium is a 1+, and acetate's a 1-. So there's the formulas for our products. The next step is to balance the equation. So we have to use some coefficients out here. I see over on the left there that we've got 2 acetates and 3 lithiums, so this is going to be kind of a mess for us. Or you can start balancing this thing out if you really want to. That's our big molecule right there. We got all kinds of things going on. Here's the balanced equation. Did you get it? It's kind of a trick, but hopefully you can look at it kind of close. Hit pause if you need to, but count the atoms there and make sure that you can see how everything is balanced here. That's a previous lesson, so I'm not going to go through a bunch of time on this right now, how that's balanced. Like I said, do your waffle if you need to and count it. All right, next part. We need to explode out all of the ions, anything that's aqueous, and then we keep together our precipitate. So what's our precipitate from our product? Well, we'd have to go through our solubility rules, but I know one of my solubility rules is that anything in sodium's family tends to be aqueous. So there's that one right there. I also happen to know if you go further down on the list of solubility rules, it says that most phosphates tend to be insoluble. So Fe3PO42 is probably going to be our precipitate here. All right, so there we go. Starting to break apart our ions. We've got 3 iron 2 ions, 6 acetate ions. Again, there's a 3 out in front, so that's going to hit with that particular subscript to give us 6 total acetates. When we take a look at our lithium phosphate, we have 6 lithium ions. Again, that coefficient has to distribute across. And then we have 2 phosphate ions for the same reason. Over on the right, our Fe3PO42, our iron 2 phosphate, stays as a solid because it is stays together as a molecule because it's our precipitate. And then we explode our lithium acetate. So with that, we've got 6 lithium ions and 6 acetate ions. So hopefully you had some success with doing that. It is a little bit tricky to manage all of these coefficients and subscripts and when do I break it apart, when do I not break it apart. Really important to focus on that kind of sequence of events. Predict your products, write your formulas for your products, balance the equation, make sure you get that part. Then at some point in time you have to check your solubility rules, see what's aqueous and what's solid or what's your precipitate. Then you got to go through that step of kind of exploding out everything that's aqueous. And don't forget, when you have coefficients and subscripts, sometimes you got to be really careful about how many ions you get from your solution here. Sorry, were you done looking at that? I didn't mean to hit the forward button. All right, ready? Okay, moving on. Okay, so take 2 here. Dog started barking. Sorry. Anyway, if we are taking a look at some of those equations, I don't know if you noticed this, but some of the ions that were on the left side of the equation were exactly the same as on the right side. It turns out in these sorts of equations, some things are actively reacting. They're forming new bonds, and they're forming that precipitate. And that's kind of interesting for us, chemically speaking. But some things really aren't. They're just kind of hanging out. They were there before, they're after. We call those things spectator ions, and they're present on both sides of a chemical reaction. So let's take a look at an example here. Here's one from earlier in the presentation where we had calcium ions, nitrate ions, potassium ions, and carbonate ions. So this was the reaction between calcium nitrate, potassium carbonate to form the solid calcium carbonate. So it turns out if you look at this really closely, certain things don't really participate in that reaction. The calcium carbonate had something going on there, but the other stuff, the potassiums and the nitrates, really didn't do anything. They didn't form any new bonds. They were there before, they were there after. The calcium and the carbonate formed a new bond, so that's kind of more chemically interesting to us than what's going on with the potassium and the nitrate. So when we are going a little bit further, we want to identify these spectator ions. They're really not doing anything, so we really don't need to write them in certain types of reactions that we're doing. So if we take a look at this really closely, here's the other one that we've got. Is that crazy long one. We want to take a look at identifying what's been present on both sides. So here we go. Let's identify some of these spectator ions. So if we look in that first one, you can see that nitrate's present on the left and on the right. And on the other one in that equation, can you figure out which one it is? It's potassium, right? Potassium, there's 2K on the left and there's 2K on the right. They're really not doing anything. It's the calcium and the carbonate that are coming together to form the calcium carbonate precipitate. So we want to write a different, little shorter version of this equation to kind of help us figure out what's really happening. Where's the chemistry really occurring? And same thing down in the bottom. We look at this even longer one. We see that there's lithium ions present on both sides. And the other one that's present that doesn't really change is the acetate ions. They're there before, they're there after. It's the iron and the phosphate that's really doing a chemical reaction, forming a new bond. So with these, what we're trying to do is we're going to actually write a type of equation that shows what's there. So here's that same equation from the previous page. So I kind of highlighted the ones that are really important. The calcium and the carbonate are the ones that do the precipitate. So when we write this out, we can actually, kind of like in algebra, cancel out the things that are on the left and the right. And we can write a summary equation that only shows the things that are participating in bonding. So that's called a net ionic equation. We're sort of capturing just the things that are reacting together. It's a lot shorter than that complete ionic equation, which is kind of a relief. So here's another crazy long one. I'm going to let you hit pause and take care of this one. See if you can cancel out, identify the precipitate. We'll identify the precipitate, but then I want you to cancel out the spectator ions. Make them go away. So hit pause if you want to, but see if you can figure out what the final reaction, the net ionic equation for this would be. Ready? So our 6 acetates are present on both sides, so we can cancel them out. And the other one that cancels out is our 6 lithium ions. There they are. They're gone. So really our final equation, the net ionic equation, is just 3 irons plus 2 phosphates to make Fe3PO4 There it is. Net ionic equation. So keep in mind when we're writing these equations, it's kind of like a summary equation. It's showing the highlights for the formation of the precipitate. This is the new bond formation. So this is the actual chemical reaction that's occurring. The other ions are there. They really are present, and they're present in the solution, but they're not really reacting. So when we write this type of an equation is a shortcut to show us the chemical equation, but it's a little bit sometimes too short because it doesn't always show us the ions that are present that are there before and after. So there's uses for both kinds, the complete ionic and then the net ionic. So there you go. This is a summary equation called the net ionic equation, right? So there you go. Here's our kind of our final kind of summary of what we did today. So number one, we took a look at the difference between soluble and insoluble compounds. That soluble compounds exist as ions because of dissociation, but insoluble things, precipitates, exist as molecules. So then the next part, when we start to write these out in balanced equations, we need to be a little bit careful. A complete ionic equation more accurately shows which species exist as ions and which species exist as precipitates or as solids, molecules, I guess if you want to use it that way. In this case, we're going to show every species that's present in the container. The only species that doesn't get shown is the water that everything's dissolved in, because it's definitely not reacting. It's sort of in the background, so we don't include that at all. But other than that, we're trying to write every single ion that's present, and then we kind of highlight the one solid that's present as well, the precipitate. Third thing, moving forward to get a little bit more sort of in focus on what's going on in the chemical reaction itself, is we would identify spectator ions. Spectator ions are things that are present on both the left and the right, not participating in the chemistry. They're just sort of hanging out and observing, hence the name spectators, right? And then the last one is the really short summary equation, the net ionic equation, that just highlights the chemical reaction that's occurring. Which 2 ions got together, formed a new bond, and created a precipitate. Those are the ones that settle out to the bottom, and the net ionic equation really focuses in on just that particular piece. So there you go. I hope you got a little bit better insight into how to write complete ionic equations, the net ionic equations, as well as maybe what some of the benefits and maybe downsides of each type of reaction are. All right, there you go. In the last one of the unit here, we're going to take a look at some other kinds of equations that are out there as well. So hopefully you're just super excited to tune into the next one, right? See you next time.